Hey guys, good to be here. My name is Sven. I'm one of the co-founders of Light Protocol, and I'm going to try and show you today a little bit about what's going on Solana with regards to ZK. So Light Protocol is, just real quick sort of overview, a zero-knowledge infrastructure layer on Solana, and you might have heard about ZK compression. It's the primitive underlying Light Protocol that we recently launched on testnet together with our partners, Helios Labs, one of the bigger RPC providers on Solana. And specifically what we're focusing on at Light Protocol is scaling Solana through making data storage cheaper. So I'll probably have to give a little bit of context here for those of you. Actually, quick show of hands. Who's built on Solana before? Raise your hand. Okay, 2 people. Awesome. Roughly, okay, that's minority, but right. The context here is that on Solana, it's very important, is that compute is extremely cheap, like very, very cheap. Rove 16 verification on-chain on Solana, fraction of a cent. But data storage is really expensive. And I'll give the example here, and the context is, on Solana, we have these buckets of state, and it's distinguished from the actual compute. So compute is just like arbitrarily priced very cheaply. But for data storage, Solana validators, you know, it's stateful. They have to keep all the different accounts that exist and the current state of it around in RAM. And these accounts, these buckets of state, you just can think of them as just plain key value stores where an address maps to some piece of data, and there's no state localization, right? And so validators keep that state around, and that's sort of that cost is brought onto the developer and the user for something called rent. Rent is more like a bond, actually. It's when you allocate a new account. For instance, you want to create a new token balance. You have to put some SOL into the account to make it, to have the validators keep it in the actual state. And so, for reference, if you want to create a 1 million token accounts on Solana, roughly $400,000 right now. Depends on the SOL price and where it is, but it's pretty expensive, especially when you consider that the actual compute needed for these transactions to bring these token accounts to life and like create a big airdrop, etc., is less than $100. Now with compression, with ZK compression, we bring that down to roughly a little bit less than $100. So quite large multiple orders of magnitude of cost improvement for applications building on Solana, and especially those applications that want to scale to a lot of users. The other thing about Solana is, like with any stateful blockchains, that state growth is a sort of unaddressed problem. You guys have that in Ethereum land as well. There's the concept of stateless clients, etc. And arguably, ZK compression is very much a stateless client or stateless execution environment implementation for Solana. State growth, just being, for context, on Solana right now, every day there's more than 1 million new accounts being created, and there's roughly 500 million accounts just total state right now. Obviously, as time goes on, that scales, and there's actually some, physical limits that eventually you'll hit if you have, too many accounts that you need to load into a single block for, evaluating transactions. There's just some throughput limits that you hit at some point. And so state growth is a problem, and we set out to basically solve these two things, right? Like expensive data storage and state growth with ZK compression. And effectively what it is one, first it brings state localization to Solana. So you can think of Light Protocol and ZK compression as this bridge contract, bidirectional to or escrow to the localized state representation, and then it's actually a forest of many Merkle trees. And the secret, and effectively what it allows that is that you can commit to state in Merkle trees, just binary Merkle trees. We use something called concurrent binary Merkle trees that allow for a little bit more concurrency. And we use index address space trees to allow for efficient exclusion proofs, not only inclusion proofs of state. And so effectively what allows this is that you can commit to state, you can store that state somewhere else, not in the on-chain account space. And what we do is, well, by default, we just, similar to like something like blobs or call data, we just like dump it onto the Solana ledger, it goes into the history, you can index it, has the same, same safety assumptions with regards to DA as Solana itself, but obviously you need indexers to keep that state around, right? Similar to something like inscriptions. And then the third element that makes this possible on Solana at sort of the scale that we do is we actually use Poseidon hashes. So there's a Poseidon hash Merkle trees all the way. And so we can actually create very fast snark proofs on top of that data. And to give you one example, and I'm going to show you a little demo in a minute to show you just how fast they are. So, if there are any questions until by now, or nothing, cool. Let me just go ahead and do a little bit of a demo. Someone could do me the honor. Thanks. So I'm gonna open up the terminal. We have this. We have a CLI here. And I just installed the NPM package, ZK compression CLI. And what I'm going to do is I'm just going to create a new token, mint, that is compressed, and I'm going to do a simple transfer. Actually, do this. Do a little a compressed transfer. And basically what you'll see is that it's very close to like synchronous ZK, if you will, because each transaction creates a snark. So let's go ahead and do this. So first of all, I'm going to check what my address is on Solana. I will need that. And then I'll go ahead and I'll start I'll start the light test validator. And this will take a while, I'll do a bunch of steps. But effectively what this does is it creates a local copy of Solana, like a local Solana, single node Solana cluster on my machine. And it also starts up an indexer that indexes these compressed state transitions. This indexer is built by Helios Labs. It's open source. You can run it yourself. I'll show you here. And then the third thing it does, it also starts up a NOC prover node, which we will use to create snarks. And just to give you context, these snarks are then proving inclusion of state that we committed to previously. And so we can send the data on-chain in a transaction, read from it, just like any on-chain data in a smart contract. We just need to write that validity proof that says, well, that state was previously committed to. Yeah?
What is the prover node?
So the prover node gets the index, so someone needs to index the state commitments, and then the prover, and the prover node takes Merkle proofs of the state commitments and batches them together into a snark. And I'll give it a little bit of context here. The reason we can't just do plain Merkle proofs is because there's a transaction size limit on Solana, which is capped roughly 1 kilobyte, right? So you need a small witness, and that's what we do with snarks. You could do like a Plum KZG commitment as well. Snarks is just time to market, more flexible. And then we also, by the way, we do something like we use curve compression to decompress the snark itself on chain, so we can actually cut it to 128 bytes, right? So the proof size is very succinct. We don't use it for the ZK element, we use it for succinctness, and allows us to prove a lot of state inclusions, exclusions inside one transaction. All right, so I'm going to create a mint. It's going to create a random mint here. I'll just need to keep track of the public key here.
Sorry, just to be absolutely clear, if I understand the previous point right, we are not the sorry, what did you call it? The relayer node or prover node?
Yes.
The prover node does not provide privacy. No ZK part, just the snark part of it.
Yes. So this is really focused on compressing the Merkle proofs, right, and Merkle proofs into one 128 byte proof. 2 signatures, very small.
Got it. Thanks.
Cool. Thank you. Awesome. Thanks. Okay, cool. So I'm gonna mint some tokens that I just created, like a token mint, 9 digits, default settings, to myself. That's actually wrong. To myself. We had that address somewhere here. Thank you. And then I'm just going to do 42. And then, of course, I need to define a mint as well, and we have the mint right here. So now I have a bunch of compressed tokens. I can check that right away. I'll just need to type, actually I need to type light balance to see my compressed balance, my owner key, and then the mint I need to define as well, because I want to see the mint, the balance of this mint here. And then we see, okay, now I have 42 compressed tokens of that mint. And now I can go transfer it. So actually I need a new key. Let me see. Let me go find a Solana address. Oh, here we go, okay. So I take that Solana address here, and I'll execute a transfer to this Solana address. I'm gonna transfer 21 tokens, and I need to define the mint as well. And we have the mint right here. And there you go, that was a compressed transfer. And the transfer created a proof. And you can see, so to give you context here, execution time, 800 milliseconds in total with all the overhead. And the proof generation time that we have with our NOC prover, I think we measured this on an M1 Pro, was per compressed account inclusion that you want to prove or exclusion, roughly 20 to 30 milliseconds. So very, very fast, and it feels, it's actually, I would say, a good case for like consumer grade ZK. That was basically the demo. Thanks. And I think just lastly, I think just want you to take this away. Solana is awesome for ZK. Very cheap proof verification. Now we have a bunch of these primitives and syscalls in the Solana runtime, including Poseidon hashes, including AltBM128 and AltBM128 proof compression right in the runtime. And then now also with compression, what effectively this is now you have all the L1 shared bridge contracts, all the plumbing to the Merkle trees. You can keep your state root, you can dump it into a compressed account if you will, and then you can interoperate through this shared infrastructures as long as you opt into the same contracts and the same RPC and follow the same account layouts that we enforce on the protocol level. And now you can build whatever application you want. You could decide to encrypt your DA, right, and move more of the proof into your custom. Like you can verify a custom proof, and you have a client-side smart contract. This can be anything really, from private transactions to rollups, whatever you want to build. So that's my call to action. I hope that you guys will consider deploying to Solana and sort of help push the ZK forward there as well. Thanks.
So Oh, this is great. Really bullish on CK on Solana, by the way.
Awesome.
So which particular proving system are you using?
So that's just Growth 16. So as I said before, you could build something more bespoke with, so what we have in the Solana runtime now that makes proof verification very cheap is the LPM 128 syscall,
Yes.
elliptic curve. So you could go with some other, build something else, but we use Growth 16.
Right. Yeah, I suppose Growth 16 could work there, but also like Halo 2 or anything else, right? And
Sorry?
which also Halo 2 could work for
You
that.
could, yeah, you could, the reason why we use Growth 16, even though it's like so old, is it's extremely succinct, and that's what we need.
Exactly. I see. And which exact implementation of Growth 16 are you using?
I can dig up the specific implementation. Actually, we can.
Gnark?
Yeah. So this, what I showed you, uses NARC. So the prover node is a NARC prover node, but a previous instance, which this is not, we just use Circom.
Snark.js's implementation of
Yeah, that was like the very first step. Yeah.
Oh, I see. Yeah, that's pretty good. We're working also on like, so there's like an standardization effort for Growth 16 proofs. There's people that want to deploy like Growth 16 verifiers on using C++ Solidity and Rust and all of that on other chains, so like Bitcoin as well, Dogecoin. And is there like a Growth 16 verifier implementation on Solana yet? Do you know?
Yeah, it's open source, so we have to create open source. Let me just show you the repos right here. So here you have the mono repo. It's just light dash protocol. No, it's actually one light protocol on GitHub. And then, as you can see here, here's an open source crate, Growth 16 Solana.
Oh, that's awesome.
Yeah, and then for the specific NARC instance, if you want to reuse the Merkle proofs, we do have a light verifier crate as well that you can use.
I see. Okay, awesome.
So if I were to use this on-chain verification, can I just what does the stack look like for a developer? Should I just write the proofs on Circom or something like that? What does the stack look like?
Yeah, so previously we had built private smart contract execution. We had this whole like macro Circom tooling, etc. We actually dialed that down to pivot to just like compression. So right now this is super agnostic to what you do to verify your own custom ZK proof if you want to build a client-side smart contract, right? So you'd probably want to go with you can use Circom, but I'm personally really excited about some of the ZK VMs potentially deploying on Solana, like RIS0, Sixings, SP1, and then a couple of others as well that are currently in the works. Cool. Thank you guys. And then if you want to text me on Telegram, it's just Swen, SWEN_light. All right, thanks.